forgot to mention that the horizontal displacement actually has a special word, and we call it the range. Okay, so it's kind of like a firing range. You know, it's the distance that the object travels in the horizontal. So we move now to the vertical part of the motion, the one that's affected by gravity. And you may be familiar that the acceleration in the vertical direction is actually not zero. It has a value near the surface of the Earth of 9.8 meters per second squared. Now, if you go somewhere else, like maybe the top of Mount Everest, then that value is actually slightly less than that, at about 9.6 meters per second squared. So you can see, back to our initial discussion, that in reality the gravitational field is not 100% uniform. But of course Mount Everest is about 8.5 or 8.8 kilometres up, so that's a mighty good throw if you can throw it that far. All right. So in the vertical motion, we do now have an acceleration that we need to consider. And so all three of the equations of motion now apply. All right? So we would just be substituting the acceleration of gravity of 9.8 meters per second squared into there. Now, one of the key points to remember with this kind of analysis is that you must put horizontal values in horizontal formula and vertical values in vertical formula. And on that, we need to consider first of all, what are the horizontal and vertical values when we actually launch the object. All right, so we've launched the object at 45 degrees. All right, so we've just thrown the object like that. We've applied a force with our hand. Now we're looking at the point at which I release the object, just there, is where we're going to be analysing our motion. All right, so from there it starts to move freely in the gravitational field. All right, now that initial velocity, all right, can be understood as being made up of a horizontal part and a vertical part. Alright, so over here with these equations, you've had your initial horizontal velocity, but you also have your initial vertical velocity. And those two aren't actually real in a sense. It's not like the object is going up and across, up and across. We actually combine those two into the actual velocity, v0. Right? But the advantage of breaking it up into its parts or its components, as we understand them, is that we can then analyse the motion in the horizontal direction and the vertical direction separately. Alright? So we need a little bit of trigonometry here to help work out what the two components are. So just a little bit of revision here. So remember, sine of an angle is equal to the SOHCAHTOA, toa, and remember that. Sine equals opposite over hypotenuse. Right, which is V0 V over V0. So we can rearrange that. And we can see that the initial vertical velocity is going to be the actual launch velocity multiplied by the sine of its launch angle, which in this case is 45 degrees. Alright? And similarly, cos 45 is the adjacent over the hypotenuse. V naught H over V naught. So rearranging that, the initial vertical velocity can be understood as being V naught times by cos of 45 degrees. Now, if we had an angle other than 45 degrees, let's just say it's angle theta, then our formula, our generalised formulas, become those two. And with that information, now you can actually set about solving some problems with projectile motion. So good luck.